tonight something slipped into our solar system and broke a rule we thought was unbreakable. This is 3I Atlas, an interstellar visitor, and in the last few days it started doing something no comet has ever done. Not in the textbooks, not in the simulations, not ever. If the numbers are right, it shouldn't be possible. And yet telescopes are catching it live. Is it shedding mass in a way we've never seen? Spinning itself inside out? Or is this the first clue that comet isn't even the right word? Let's dive in. It started with a tiny blip in a crowded star field. Not a dramatic streak, not a fireworks show, just a whisper on a camera that's designed to catch trouble before anyone on Earth even knows it exists. On July 1st, 2025, the University of Hawaii's Atlas telescope at Rio Hurtado, Chile, flagged an object moving too fast and too strangely to belong to us. Within hours, astronomers realised they weren't just tracking another local ice ball falling towards the sun. They were staring at a one-way traveller from another star system. That's how 3I Atlas entered the story. From the first measurements, its path refused to curve into a neat loop. Plot the motion backward and it does not wind around our sun. It sails in from the deep, skimming through like a tourist who never booked a return ticket. Astronomers call that a hyperbolic trajectory, and it's the fingerprint of an object that formed under another sun and was flung into interstellar space long ago. In plain terms, this thing is not from here. Only 2 other visitors like this have ever been confirmed. One I/Oumuamua in 2017, and 2 I/Borisov in 2019. 3I Atlas makes it number 3. The name tells you the whole plot in 3 characters and a word. The 3 is the third of its kind, the I marks it as interstellar. Atlas honours the survey that first reported it. The discovery wasn't a single snapshot either. Once astronomers knew where to look, they dug up earlier, pre-discovery images from other Atlas stations and Caltech's Zwicky Transient Facility, extending the observational arc back into mid-June and nailing down the path with far more confidence. The more they tightened the orbit, the clearer the message became. An outsider is passing through. Right away, NASA and ESA queued up their big eyes in space. Hubble locked on July 21st and resolved a teardrop-shaped haze, dust lifting off a solid, icy heart that Hubble still couldn't see directly. Even so, those images let scientists bracket the nucleus to somewhere between a few hundred meters and a few miles across, while 3I Atlas tore along at roughly 130,000 miles per hour. Fast, small, active, and absolutely alien. If you're wondering about danger, there isn't any. 3I Atlas never comes close to our planet. Its minimum distance from Earth stays out around 1.8 astronomical units, farther than the Sun is from us, and its swing past the Sun happens just inside Mars's orbit. It's the cosmic equivalent of a high-speed flyby on the opposite side of a stadium. Thrilling to track, safely distant to watch. What makes this particular visitor irresistible is timing and geometry. It approached from the general direction of Sagittarius, near the Milky Way's crowded heart, which partly explains why it hid so well in the glare of countless background stars until late June. Then it threaded a path that took it past Mars in early October and behind the Sun in late October, temporarily ducking out of view for Earth-based observers before reappearing in early December. For mission planners and telescope teams, that dance is an opportunity to watch an interstellar comet change in real time as sunlight wakes it up. For scientists, 3I Atlas is more than a headline. It's a precious third data point. Oumuamua looked nothing like a classic comet and left frustratingly few clues. Borisov behaved more like the comets we know and as if it had been copied from our own backyard. Now, with 3I Atlas, researchers can test which traits are universal to small bodies born around other suns and which are quirks of a single system. Every measurement, brightness, dust behaviour, speed, spin, chemistry, helps sketch a family portrait of worlds we can't yet see directly. The Atlas network's quick trigger and the flood of follow-up observations also show how far we've come since 2017. Today, when the sky twitches, dozens of robotic eyes on mountaintops across multiple continents pounce, and space telescopes pivot like a pit crew. Hubble, Webb, Spherex, Swift, and even spacecraft around Mars are lining up to eavesdrop on the same traveller from different vantage points. It's coordinated astronomy at galactic visitor speed, and as 3i Atlas races inward, its behaviour is already hinting that we should expect the unexpected. Astronomers are watching for how its coma grows, how its dust acts, whether familiar gases appear in the usual order, and whether something about its far-from-home origin changes the script we've learned from our domestic comets. The closer it gets, the louder those clues become, and the story it's whispering is about to turn strange. Why does this visitor matter so much? Because every interstellar object is a sealed time capsule from another sun, a tiny piece of an alien planetary system that somehow broke free and crossed the dark to get here. We can't fly to those distant systems yet, but sometimes a fragment of them flies to us. That's the gift. With 3i Atlas, we finally have a third sample to compare, after the baffling first guest, Oumuamua, and the textbook comet second, Borisov, which means we can stop guessing from two anecdotes and start seeing patterns. Think of interstellar objects as postcards that weren't meant to be mailed. When giant planets jostle young systems, countless icy rocks get tossed outward forever. A few drift into our neighbourhood, carrying the chemical fingerprints of their birthplaces, which ice is formed, how dusty the protoplanetary disk was, what temperatures the grains felt, even how violently they were thrown out. Oumuamua arrived without a visible halo of gas or dust, and then nudged off course in a way many scientists now attribute to subtle outgassing. Mysterious, borderline paradoxical for something that looked asteroidal. Borisov, by contrast, behaved like a classic comet but with a twist. It was loaded with carbon monoxide in amounts far higher than most comets we know. Those two data points already told us that other systems can make small bodies very unlike ours. 3i Atlas gives us the tiebreaker. Why a tiebreaker matters? With just one strange guest, it's an oddball. With two, it's a coin flip. With three, you can start asking population questions. Do most interstellar visitors shed dust like Borisov or stay tight and enigmatic like Oumuamua? Do they carry the same easy-to-vaporize gases in the same proportions? Or does each system stamp a different recipe onto its comets? Are their dust grains fluffy and polarizing in the same way as our comets? Or do they scatter light differently? Early looks at 3i Atlas already hint at some unusual optical behaviors, like reports of distinctive polarization and an anti-tail, suggesting the dust may be arranged or released in ways we don't often see here. That's exactly the kind of clue you need to tell how an alien comet was assembled, layer by layer, grain by grain. And then there's the origin story. Ejection from a home system isn't gentle, it takes gravitational pinball with giant planets, or a star's tidal shove, to fling an object onto a one-way path. By measuring 3i Atlas precisely, its trajectory, brightness changes, and how its dust behaves in sunlight, astronomers can rewind the tape and estimate the kind of environment that built it. Did it form in a frigid exokuiper belt, or closer in and later migrate outward? Was its dust baked, shocked, or barely warmed? Each of those histories leaves different textures in the grains and different perfumes in the ices, signatures we can sniff from millions of kilometers away with UV, visible, and radio telescopes. Remember how Oumuamua forced a rethink of what counts as a comet? No obvious fuzzy coma, a wild shape, and a tiny non-gravitational push that launched every explanation from trapped hydrogen to exotic ices to sunlight pressure. Then Borisov reassured everyone that yes, interstellar space also produces normal-looking comets, except its carbon monoxide was off the charts compared to typical locals, which means the freezer where it formed was far colder or richer in CO than ours. Put those together and you get a picture of staggering diversity. 3i Atlas is the first chance to test whether that diversity is the rule, not the exception. This matters for a deeper reason. Small icy bodies are couriers of ingredients. In our own system, comets and their cousins are thought to have delivered organics and volatiles to young worlds. If visitors like 3i Atlas carry different mixes of gases and dust, that hints at how other solar systems seed their planets, and how often the raw materials for habitability get spread around. It turns planetary science into comparative planetology at interstellar scale. Not just how did Earth get its stuff, but how does any Earth get its stuff? There's also a practical revolution underway. A decade ago, catching a single interstellar object felt like a once-in-a-century fluke. Now, wide-field sky surveys automate the hunt night after night. The new Vera C. Rubin Observatory is spinning up a 10-year movie of the sky that's expected to pull in a trove of fast movers, possibly dozens more interstellar passers-by over the coming years, depending on who you ask. That shift, from rare surprises to a steady trickle, turns these visitors from curiosities into a population we can actually study with statistics. 3i Atlas arrives right as that door is opening, and for the first time we're preparing to meet the next one up close. ESA's Comet Interceptor will wait out at the Sun-Earth L2 point, ready to sprint toward a newly discovered long-period or interstellar target and split into multiple probes for a 3D flyby. The mission is designed for exactly this era, a sky full of alerts and one chance to pounce when a fresh visitor dives in. Every oddity 3i Atlas reveals helps mission planners tune which targets are worth chasing and what instruments should be pointed where. For observers on the ground, 3i Atlas is a laboratory in motion. Polarimeters watch how dust twists light, spectrographs comb the glow for chemical barcodes, and high-cadence imagers track how jets and streaks evolve night by night. Each technique tugs on a different thread. Grain sizes, fragment speeds, rotation periods, whether the nucleus is sturdy or shedding. Because it's interstellar, every one of those threads leads back to a disk and a star we'll never see directly, and yet through this visitor, we can read its weathered history as it rushes by. Even the path matters. A hyperbolic arc isn't just fast and gone, its exact tilt, speed, and timing tell you where in the galaxy this thing could have wandered and for how long. Stack enough of those arcs from enough visitors and you begin to map the invisible river of small bodies flowing between stars. With 3i Atlas added to the tally, that map sharpens, the questions get bolder, and the next alert will land in a world better prepared to listen. Here's the reveal you've been waiting for. While still nearly 3 times farther from the Sun than Earth, 3i Atlas is already spraying water into space. NASA's Neil Gehrels Swift Observatory caught the unmistakable ultraviolet glow of hydroxyl, OH, the telltale breakup product of water molecules. Even at about 2.9 astronomical units, Swift measured a torrent on the order of 40 kilograms per second, which scientists liken to a fire hose at full blast. That is wildly early for water to turn on, and it's exactly why observers are buzzing. How do you see water on a dark speck from another star system? You don't look for droplets, you look for fingerprints. Swift's ultraviolet optical telescope stared at 3i Atlas during 2 carefully timed runs, July 31st to August 1st and August 19th, 2025, and stacked scores of short exposures to drag a faint signal out of the noise. In those stacks, an razor-thin emission near 3085 angstroms popped out, OH freshly carved from H2O by sunlight. From orbit, Swift can see this ultraviolet band that Earth's atmosphere blocks, which is why the detection had to happen in space. Here's why astronomers did a double take. At that distance from the Sun, most comets are still sleepy. Surface water ice should be too cold to vaporize efficiently, so classical sun warms the ice, ice turns to gas, doesn't cut it. The working picture is more intricate. Sunlight lofts tiny icy grains off the nucleus. Those grains heat quickly and vent water in the coma itself, feeding the OH signal even while the surface stays too cold. That kind of grain-driven water source has been seen only in a handful of distant comets, and never this clearly for a visitor from another star system. The numbers matter because they rule out hand-waving. A sustained outflow around 40 kilograms per second when 3I Atlas was still far from the inner solar system means there's either an extended reservoir of icy dust or unusually efficient mechanisms flicking water into space. Both options point to complex, layered ices that preserve the comet's formation history like rings in a tree. Another eyebrow raiser. Water showed up before the usual suspects. In many comets, observers first flag easy tracers like cyanide CN long before a strong water signature in the UV. With 3I Atlas, Swift's OH detection came prior to clear CN reports, a reversal that hints at a different mix of volatiles or dust grain physics. Not long after, large telescopes did begin to see CN building, but that early water-first moment is a big clue about what's really driving the activity. Ground-based teams then added texture to the story. Using the Very Large Telescope, astronomers reported incipient CN outgassing as the comet closed in from about 3.17 to 2.85 AU, and, intriguingly, bright nickel lines without comparable iron, an odd chemistry twist that suggests nickel may be liberated from dust by gentle processes rather than blasted straight off metal grains. That doesn't change the water result. It widens the mystery about what kinds of stuff are being stirred into the coma and how. If you're wondering how certain the water call is, the spectral line is the community's gold standard tracer for H2O, and the detection came from 2 separate visits weeks apart. The precise production rate depends on modelling choices, like how much dust reddens the light, but the presence of water vapour isn't in doubt. It's baked into the ultraviolet data themselves. And remember, Swift didn't just get lucky. The telescope sits above the atmosphere where OH's ultraviolet signal isn't smothered, so it can spot water activity before the comet gets close enough for the ground instruments to see the usual visible light gas bands. That's why this detection dropped while 3I Atlas was still far out, rewriting the timeline for when an interstellar comet can turn watery. Put these threads together and a picture starts to form. 3I Atlas isn't merely waking up, it's venting water early and vigorously, probably through swarms of sun-warmed icy grains that act like countless micro-geysers. As larger observatories keep watch on tracking how OH evolves, when CN catches up, and whether carbon dioxide or carbon monoxide are pushing dust off the surface, each new spectrum will either tighten or overturn that grain-driven story, and the next window of Swift time is already primed to listen. To catch water around a dim speck from another star, you don't point a big ground telescope at it and wait. You go above the air and listen for a very specific whisper. NASA's Neil Gehrels Swift Observatory carries a small ultraviolet optical telescope that's perfect for this. In late July and again in mid-August 2025, the team aimed it at 3I Atlas and took dozens of short 3-minute snapshots. Back on Earth, they aligned those frames on the comet's motion and stacked them into deep images, pulling out signals far too faint for any single exposure. In the ultraviolet stack, a narrow glow appears near 308 nanometers, hydroxyl, the fragile fragment that sunlight carves from water. That glow is the giveaway. It's not a hunch or a rumour. It's water announcing itself in the only part of the spectrum that Earth's atmosphere normally hides. Ultraviolet is the key because the air above us is a jealous gatekeeper. Ozone soaks up much of the near UV light, including the exact wavelengths where hydroxyl shines. From orbit, Swift can see what ground observatories cannot, making it one of the few instruments that can catch water turning on long before a comet gets close to the Sun. With 3I Atlas, the first observing window, July 31st to August 1st, offered a tentative detection. The second window, August 18th to 20th, sealed it. A clear band of OH emission that leaves little room for doubt. 2 visits, 2 independent looks, the same fingerprint, now bright enough to measure. Turning brightness into physics is a bit of detective work. Each OH molecule acts like a tiny neon sign whose glow strength in sunlight is well calibrated. Measure how bright the comet's OH halo is, subtract the background, and, using standard comet models, you can estimate how many water molecules must be breaking apart every second to sustain that glow. In August, when 3i Atlas was still nearly 3 times farther from the Sun than Earth, that calculation came out to roughly 1.3 times 10 to the 27th power molecules per second, about 40 kilograms of water every second. Reporters reached for a vivid comparison and landed on a fire hose at full blast, which is exactly what the numbers feel like for a comet so far from the furnace. What makes that number so startling isn't just its size, it's the distance. Classic comet playbooks say surface water ice should be mostly inert out there. So why is 3i Atlas already throwing off water? The UV data point to a culprit you can't resolve directly. Swarms of tiny icy grains. Sunlight lofts these grains into the coma, where they warm quickly and vent water on their own, away from the nucleus. Because Swift saw OH before many of the usual optical gas tracers showed up, the sequence hints that grain-driven water may be leading the dance this time, with other gases joining the chorus later, as the comet moves inward. Technically, pulling this off with a 30cm telescope is its own kind of magic. The team built deep stacks totaling about 2.3 hours in the UV and approximately 42 minutes in visible light, carefully registered on the comet to avoid smearing the signal into the starfield. The ultraviolet images reveal the OH halo. The visible images help track dust and set the colour reddening assumptions you need to translate raw counts into real-world water loss. Those details matter, because the answer depends on how dust modifies the light, and the authors are explicit about how the rate shifts with different, reasonable choices. Even under conservative assumptions, the second epoch detection lands squarely in "this is real water" territory. Swift's vantage point also gives astronomers timing leverage. By catching water this early, they now have a baseline to compare with what larger facilities will see closer to the Sun, in the near-infrared for ices, in the optical for gases like CN, and later in the ultraviolet again when geometry allows. That continuity is a big deal. It lets researchers watch the OH halo grow, fade or shift, and tease apart water coming straight off the nucleus from water coming off those sun-warmed grains. The ultraviolet fingerprint is the anchor that keeps all those follow-up measurements tied to a single, unambiguous tracer. When you hear ultraviolet fingerprint, imagine a crime lab for comet gas. Sunlight hits water molecules, they split, and one of the fragments, OH, fluoresces at a specific set of UV wavelengths. Swift is tuned to see that faint afterglow. With 3i Atlas, the glow wasn't just there, it was there twice, weeks apart and stronger the second time, exactly what you'd expect from a comet waking up as it falls inward. That's how we know we're not being fooled by dust tricks or random noise. It's the same method comet scientists have used for decades on local comets. This time the lab sample happens to be from another solar system, and because the measurement is quantitative, it folds directly into the bigger story. The team can infer the minimum active area required to sustain that water flow and flag that, proportionally, 3i Atlas looks unusually lively compared to many comets born here. Pair that with early reports of cyanide emerging later on, and the picture sharpens. Water is leading early, other gases are catching up, and the ultraviolet channel is the reason we notice the head start at all. Above all, the ultraviolet detection gives astronomers a common ruler. Water is the yardstick for comet activity. Once you have it, you can compare 3i Atlas to Borisov, to our Oort cloud comets, and to whatever interstellar wanderer shows up next, using exactly the same scale. That's how a faint 308 nanometer glow turns into hard numbers, and how those numbers turn into a story about an object that didn't form under our sun, and yet is telling us plainly what it's made of. Water shouldn't be this bold, this far from the sun. At nearly 3 times Earth's distance, sunlight is weak, and the surface of a comet ought to be too cold for easy boil-off. Yet 3i Atlas is clearly exhaling water, and the simplest sun warms ice turns to vapour story doesn't fully explain it. The clue is in the way the signal appeared. Swift saw the ultraviolet fingerprint of OH, the daughter of water, while the comet was still out in the cold. That flips the usual script and forces us to look beneath and above the surface for the real driver. Start with the physics every comet scientist keeps in their back pocket. Other ices wake up sooner than water. Carbon dioxide and carbon monoxide are far more eager to sublimate in the deep cold, and when they do, they act like tiny rocket engines. As those super volatiles seep out, they can push loose material off the surface, everything from dust to snow-like clumps. If some of those clumps are true icy grains, they warm quickly once they're lofted into sunlight and vent their own water right there in the coma. That turns the space around the nucleus into a halo of microgeysers, which is exactly the sort of extended water source Swift's data favour at these distances. For 3I Atlas, this is the independent support for this sequence. Early spectra indicate a carbon dioxide-rich coma, one of the highest CO2 to water ratios ever seen, which means CO2 is plentiful enough to do the heavy lifting and fling icy grains off the surface. Once those grains are sunlit, water shows up even while the nucleus itself stays too cold to drive the show alone. This is a classic way to cheat the cold. Let a more volatile ice do the pushing, then let the grain cloud do the watering. There's another lever nature can pull, the architecture of the surface itself. Comets are not smooth billiard balls, they're dark, porous and patchy, with crusts that can insulate some regions while cracks and vents connect others to space. Gas can build below a dusty mantle and escape through pores and fissures, focusing into jets that lift material without needing the whole neighbourhood to heat up. Laboratory and modelling work shows that even modest porosity and a thin dust layer can localise sublimation, turning gentle heating into efficient gas escape. If the mantle over 3I Atlas is fragile or shot through with channels, you don't need much, it's just CO2 to loft a steady drizzle of grains. And then there's the wild card hidden in the ice's crystal structure. Water ice can form in an amorphous state that traps other gases inside like bubbles in a frozen soda. Warm it enough, still well below the threshold where water itself would normally sublimate, and it rearranges into crystalline ice, releasing the trapped gases and a little heat in the process. That trigger can open pathways, increase pressure, and set off gentle venting or sudden puffs long before classic water-driven distances. Amorphous to crystalline transitions have been proposed for distant activity in multiple comets. If 3I Atlas carries amorphous ice from a very cold birthplace, the same mechanism could be priming the pump now. Observations line up in a telling order. Swift's OH detection came first when 3I Atlas was still far out. Only later did ground-based telescopes begin to pick up cyanide, a familiar tracer that usually shows early in many comets. That reversal hints that water is being fed by an extended source, those icy grains, while the usual gas chemistry ramps more slowly from the nucleus. On top of that, very large telescope spectra saw bright nickel lines with very weak iron, an odd chemistry twist that suggests some metals are being released by gentle processes from dust rather than blasted from solid chunks. Altogether, the pattern points away from a simple sun-warmed surface and toward a layered, grain-driven machine. Once you accept that the coma itself can be a water factory, the Swift measurement makes more sense. The team stacked many short UV exposures to isolate that faint OH glow, then translated it into a water loss rate on the order of a few dozen kilograms per second. At face value, that would imply a large active area if the water were coming straight off the nucleus. Far more credible, given the distance, is that much of it is coming from grains with huge total surface area spread through the coma. The grain model neatly explains how you can get a strong water signal without demanding the nucleus behave like a sun-baked geyser at 3 astronomical units. Why would 3I Atlas be so good at making and lifting icy grains? The CO2 clue is big, but grain size and texture matter too. Fine, bright grains heat fast and cool fast. Larger, fluffier aggregates can carry ices longer before they fully dry out. JWST spectra already show not just gases, but water ice signatures in the coma, consistent with the idea that grains are present and actively evolving as they ride the sunlight. If those grains started as fragile clumps in a low-gravity environment, even a whisper of CO2 could peel them off like frost from a pane of glass. There's precedent. Comets in our own system have shown hyperactivity when icy grains dominate the coma, famously Hartley 2, where CO2 jets threw out snowballs that then released water. Distantly active comets like K2 and 29P have long taught us that CO or CO2 can drive activity in the cold. 3I Atlas is stitching those lessons together in an interstellar context. A CO2-rich engine doing the lifting, a porous mantle providing the plumbing, and amorphous ice or trapped volatiles adding pressure from below when conditions are right. As more spectra arrive, watch for a few diagnostic shifts. If grain-released water is the main source, the OH halo may look broader and smoother than you'd expect from purely nucleus-driven jets. CN and other classic tracers should keep rising as the comet nears the Sun, and the surface warms enough for their parent ices to take over, tightening the timing gap between water and everything else. And if CO2 really is the backstage muscle, we should keep seeing it dominate in the infrared, while the UV keeps catching water's faint echo in the dark. The chemistry of a comet is supposed to follow a familiar script. The far-out volatiles whisper first, the water chorus swells later, and the optical gas tracers light up in a predictable order as sunlight turns the knob. 3I Atlas walked on stage and shuffled those lines. Before many of the usual visible light species made a clear entrance, NASA's Swift Observatory caught the ultraviolet glow of hydroxyl, the clean fingerprint of water being split by sunlight, while the comet was still out near 3 times Earth's distance from the Sun. The measured rate was on the order of a few dozen kilograms per second, a level of water activity that's ordinarily reserved for much warmer neighbourhoods. That early water detection didn't arrive in a vacuum. Ground-based teams using the Very Large Telescope had been watching 3I Atlas creep inward and at first found tight upper limits on typical comet gases. Then weeks later and closer to the Sun, CN finally began to show. Weak at first, but real, meaning the usual optical tracer lagged the unambiguous ultraviolet sign of water. For long-time comet watchers, that's a striking reversal of the on-ramp many comets take, where CN is often the easier early catch from the ground, and water is harder to confirm until objects warm up or you can go to space. Under the hood, the mix is even stranger. James Webb's first spectra of 3I Atlas revealed a coma dominated by carbon dioxide, with water and carbon monoxide present but clearly outgunned. The CO2 to H2O ratio was reported around 8:1, among the highest ever measured, which immediately suggested that this interstellar visitor carries a different recipe than the comets we're used to. In plain terms, the gas doing the heavy lifting in the cold appears to be CO2, not water, and that flips the usual energy budget for how dust and grains get lofted. A CO2-rich engine paired with early water is not a contradiction if you picture the coma as a factory. CO2 escaping from the surface can toss out fragile icy grains. Those grains heat quickly in sunlight and vent water away from the nucleus, creating the ultraviolet OH halo swift saw, while the ground was still waiting for the classic optical bands to wake up. In that sense, 3I Atlas isn't merely active, it is redistributing where chemistry happens, exporting part of the water production into the surrounding cloud instead of confining it to the surface. Then there's the metal mystery. As the comet brightened, high-resolution spectra recorded a forest of neutral nickel lines, but iron, usually its partner in crime, stayed frustratingly absent. That imbalance doesn't fit simple chip off a rock sublimation. One plausible path is gentle release from dust via photon-stimulated desorption or breakdown of nickel-bearing organics. The authors even point to carbonyl chemistry as a candidate, where metals hitch rides on volatile molecules that carry them into the gas. However you slice it, nickel without iron at these distances is a chemistry curveball. Shape the light and the dust tells on itself. Early polarimetric work flagged unusual polarization behavior, out of family with both high and low polarization classes of solar system comets, which hints that the grains in 3I Atlas differ in structure or composition from the usual fuzz we know. polarization is a subtle global property. It doesn't care about one jet or one clump, it cares about how the whole cloud scatters sunlight. Moving 3I Atlas into a corner of that diagram by itself is another sign that it's dust, and therefore its surface processing doesn't follow our well-trodden taxonomy. Even the geometry of the coma seems to be playing by new rules. Hubble's early look showed a sunward-skewed envelope, and subsequent imaging reports pointed to an anti-tail configuration, features you can get when dust is being shed in preferred directions, or when grain sizes and release times conspire with the viewing angle. In comets where water drives the show late, you expect the textbook tail to dominate. With 3I Atlas, the interplay of a CO2 engine, grain-released water, and evolving dust has produced a more asymmetric, sometimes inside-out seeming display. Put the sequence together the way observers actually experienced it. Swift in space nabs water's OH signature, while the comet is still deep in the cold, the ground sets tight limits, and then, later, watches CN climb. JWST weighs in to reveal that CO2 is the power broker, and high dispersion spectra lace the coma with nickel, while iron keeps its head down. That cadence doesn't just break one rule, it tangles several at once, forcing a rethink of where activity happens, on the surface versus in the coma, which molecules do the early work, CO2 over H2O, and how dust and trace metals get liberated into space. For comet chemistry, order matters, and 3I Atlas has changed the order of operations. It tells us that an interstellar nucleus can be built so carbon dioxide rich and its surface so porous or fragile that sunlight at long range is enough to loft icy grains, kick-starting water outside the usual comfort zone. It tells us that metals can enter the gas phase through pathways that don't require blasting rock apart. And it tells us, with that odd polarization and skewed coma, that the dust itself may be woven differently than the fluff we've catalogued for decades, which is why the very first thing astronomers saw was water where they least expected it, and not the optical gases that usually announce a comet's chemistry from afar. If you could scoop a jar of the coma around 3I Atlas and hold it to the light, you wouldn't see a simple water comet. You'd see a brew where carbon dioxide is calling the shots, with water both as ice grains and as vapour, very much present but not in charge. James Webb's first spectra nailed this. The gas halo is CO2 dominated, and the team directly identified water ice, gas phase H2O, carbon monoxide, and a whisper of carbonyl sulfide woven into the glow. That CO2 to H2O ratio lands around 8:1, among the highest ever measured for a comet, putting 3I Atlas well outside the comfort zone of most homegrown comets. And then there's the smoking gun for water itself. NASA's Swift Observatory caught the ultraviolet fingerprint of hydroxyl, the clean breakup product of H2O, twice in late July and mid-August, when 3I Atlas was still nearly 3 times farther from the Sun than Earth. Converting that faint glow into numbers gives a production rate on the order of 1.3 times 10 to the 27th molecules per second, roughly 40 kilograms of water every second, like a fire hose at full laugh-all blast, as several reports put it. That early vigorous water release is not what textbooks say should happen that far out. Sphere-X, NASA's new all-sky infrared mapper, added a wide-angle view, strong water ice absorption sculpting the spectrum, and an extended CO2 coma so large it can be traced across arc minutes on the sky. Their mid-August analysis places a hefty CO2 output while setting conservative upper limits on water and CO at that time, consistent with the picture of CO2 doing the heavy lifting in the cold. Crucially, Sphere-X finds that the near-infrared light is dominated by dust scattering, not the solid heart, which meshes with Hubble's tight limits, showing the nucleus itself must be small. Zoom in on the trace gases and metals and the plot thickens. As the comet crept sunward, the Very Large Telescope finally pulled CN out of the noise, weak at first, then building after the unambiguous water signal from space, which is a flipped order compared with many solar system comets. At the same time, spectra lit up with neutral nickel lines, while iron stayed elusive, a lopsided metal signature that hints at gentle release from dust or organics, rather than chunks of bare metal gassing off. It's a chemistry curveball that widens the gap between this visitor and the majority of comets raised under our Sun. Dust is its own chapter of the story. Optical spectra show a red-sloped continuum, the telltale tint of sunlit dust that many comets share. Yet polarimetric measurements place 3I Atlas in a weird corner of the map with unusually strong negative polarization, unlike typical classes of solar system comets and distinct even from interstellar cousin 2I/Borisov. Polarization is a global, geometry-sensitive clue to grain size and structure, and pushing this far off the beaten track suggests the dust here is built or processed differently. Fluffier aggregates, odd coatings, or a size distribution we don't often see. Taken together, the ingredients list looks like this: CO2 out front, water ice and vapour clearly present, an active surprisingly far from the Sun, CO alongside them, OCS riding in at faint levels, and a dust cloud whose optical behaviour doesn't fit neatly in our usual catalogues. The gas mix alone would mark 3I Atlas as unusual. Add the metals, the dust physics, and the timing of when each species shows up, and you get a composition that doesn't just differ by degree, it differs by design. Even the shape of the gas halo carries chemistry in its silhouette. Webb spectra shows sunward enhanced outgassing, a skew that hints at active regions or jets feeding CO2 into space, which in turn can loft icy grains that later disgorge water away from the surface. That's how you reconcile a CO2-dominated engine with early, robust water. The coma becomes a factory, not just an exhaust plume, and the grains themselves do part of the processing as they heat in sunlight. Meanwhile, Hubble keeps the nucleus honest. By modelling how the inner coma's brightness spreads, the team caps the effective radius at less than or equal to 2.8 kilometres for a typical dark comet surface, and allows that it could be smaller. Either way, the solid core is a lightweight compared with the sprawling dust envelope. That constraint matters when you turn gas and dust outputs into how much surface must be active, because it says most of what you're seeing is coma physics, not a giant sun-roasting snowball. If you prefer a mental checklist, here's where the evidence points right now. The primary driver is CO2. Water is abundant enough to see from the outskirts of the solar system, but much of it likely comes from sun-warmed icy grains lofted by other volatiles. CO is present, OCS is present, and CN join the party later than usual. Nickel shows up without its usual iron partner, probably released through gentle, dust-mediated pathways. The dust is red-sloped and oddly polarizing, and the nucleus is compact, hiding beneath a coma that does a surprising amount of the chemistry for us. As more spectra stack up from ultraviolet to infrared, that ingredient list will sharpen molecule by molecule, grain by grain, turning 3I Atlas from a nameless haze into the best sampled recipe we've ever had for a comet that was mixed and frozen and under another star. Catching water this far from the Sun resets the baseline for what an interstellar comet can do, and more importantly, gives scientists a common ruler to compare alien chemistry with our own. Water's ultraviolet fingerprint isn't just a curiosity, it's the yardstick comet researchers have used for decades. The fact that 3I Atlas lights up that yardstick while still out near 3 times Earth's distance means we can now anchor every other measurement — dust, carbon dioxide, carbon monoxide, even trace metals — to a number that plays by the same rules across comets. That's how one faint OH glow turns into a genuine before and after in comet science. The timing of the detection changes the narrative. Traditionally, water ramps up closer in while ground-based observers first nab easier optical traces. With 3I Atlas, Swift saw water early and decisively, then the usual CN built later from the ground. That inversion forces models to make room for a distributed source, sun-warmed icy grains in the coma, rather than a surface-only faucet. Once you accept that the coma itself can manufacture water far from the Sun, you've expanded the playbook for how comets breathe, both here and in other star systems. And then there's their composition bombshell. JWST's first spectra show a coma dominated by carbon dioxide, with water and carbon monoxide along for the ride, and faint carbonyl sulfide in the mix. A CO2 to H2O ratio around 8:1 is not just unusual. It sits among the highest ratios ever measured, and points to a nucleus that either formed near the CO2 ice line of its home disk, or had its ices processed under harsher radiation than our comets typically endure. That gives planetary scientists something they've never had before, an interstellar chemical recipe they can actually map back to formation zones in a foreign protoplanetary nebula. A second wide-angle confirmation comes from SPHEREX, which finds an extended CO2 coma and clear signatures of water ice, all while the comet was still hundreds of millions of kilometers from the Sun. Seeing the same CO2 first story with a different instrument at different wavelengths turns a startling hint into a pattern. It also tells us that the gas driving the show blankets a region far beyond the small hidden nucleus, exactly what you'd expect if jets aloft in grain swarms that later sweat water in sunlight. The order in which species appear is the clue that unlocks the mechanism. Water's OH shows up first from space, CN arrives later from the ground, CO2 is already dominant in the infrared. That sequencing is more than a trivia note. It's a constraint you can plug straight into thermophysical models, which layers must be porous, which cracks must be open, how grain sizes and sunlight exposure tune the balance between surface vents and coma chemistry. In practice, that means we can now test whether 3I Atlas is powered by CO2-rich regions that fling out fragile aggregates, or by deeper trapped gases sneaking through a leaky crust, or both. Even the trace clues drive the story forward. High dispersion spectra with the VLT catch nickel lines without corresponding iron, a lopsided metal signature that almost certainly means gentle, dust-mediated release pathways are at work. That matters because it breaks the habit of assuming a refractory elements only appear when rock is blasted or baked. It suggests subtle surface chemistry, and photon-driven processes can distill specific metals into the gas. Tie that to the CO2 dominance and early water, and you get a comet where soft physics, grain coatings, organics and light play outsized roles. Globally, the dust won't let you pigeonhole it either. Polarimetric measurements place 3I Atlas off the well-trodden tracks for solar system comets and even away from interstellar cousin Borisov. Add reports of an anti-tail and a sunward-skewed coma, and you have a geometry that encodes differences in grain size, structure and release timing. For modelers, that's gold. Polarization is a population-level constraint, not a one-jet anecdote, and it forces any successful scenario to reproduce the way the whole cloud scatters light, not just how bright it gets. All of this changes what we can ask, not just what we can see. With a water benchmark at large distance, a CO2-led gas budget, and metal and dust oddities mapped in, we can compare 3I Atlas directly to Borisov and to long-period comets from our Oort cloud on a like-for-like scale. Do carbon dioxide-rich profiles correlate with early grain-driven water elsewhere? Do nickel-heavy iron-light signatures pop up in other distant CO2-active comets once we look for them? If the answers are yes, then 3I Atlas isn't an outlier, it's the first clear entry in a new category. There's also a bigger astrobiological thread. Small bodies are couriers. They export water and organics across young systems. Catching robust water activity in interstellar space, combined with a CO2-rich engine, means other planetary systems may package and deliver their ingredients differently than ours. Whether that helps or hinders the delivery of life-friendly volatiles to rocky worlds depends on the details, grain sizes, outgassing cadence, and how long materials survive in transit, and 3I Atlas finally gives us real numbers to plug into those delivery models instead of guesses. Most of all, the cadence of observations, Swift's ultraviolet catches, JWST's compositional snapshot, SphereX's panoramic coma, the VLT's line-by-line forensics turns a once-in-a-decade visitor into a laboratory. Because the measurements are quantitative and comparable, the next interstellar object won't just add a story, it will land in a framework. If it behaves like 3i Atlas, we have a population. If it doesn't, we'll know exactly where and how it diverges. That's the part that shifts Comet research from anecdotes to statistics, from what a weird visitor to what kind of neighbourhood did it come from. And it's already forcing us to rewrite the opening chapter of the Comet rulebook. If you're picturing a brilliant sky-filling spectacle, dial that way back. 3i Atlas is a telescope target, not a naked-eye comet. Right now it's faint, around magnitude 15 by standard predictions, so even experienced observers will need a decent aperture, dark skies, and a sensitive camera to bring it out of the background. Think of it as a whisper in the noise rather than a shout across the sky. The timing makes it trickier. 3i Atlas is slipping behind the sun from Earth's point of view around late October, right as it skims its closest point to the sun. That means most of us on the ground lose it for a few weeks. It's simply too close to the glare. NASA's timeline says it reappears in early December, which is when observers can start chasing it again in the dawn sky. If you're wondering who gets a look while we can't, orbiters at Mars did. As the comet swept past Mars on October 3rd, 2025, ESA's ExoMars Trace Gas Orbiter grabbed the closest images yet. Just a soft, grainy glow zipping across its frames, but proof that the interstellar visitor was there, moving fast, and changing as it falls inward. From Earth, though, we have to wait until the comet climbs out of the sun's neighbourhood. When it comes back into view for Earth observers, don't expect a dramatic jump in brightness. 3i Atlas never comes particularly close to us. Its closest approach to Earth is about 1.8 astronomical units on December 19th, 2025, still far beyond the orbit of the Sun as seen from Earth, so the best case brightness remains in the low teens magnitudes, squarely a CCD/CMOS imaging target, and only a marginal visual object in big amateur scopes under excellent skies. Where to look, broadly speaking, as it emerges from conjunction, sky guides indicate it returns to the morning sky in early December, sliding through the constellation Virgo and then into Leo as the month goes on. That puts it low before sunrise from mid-latitudes, creeping higher each a week as the sun pulls away. An accurate finder chart from your observing site and date is essential, because at these magnitudes a few degrees off means no comet. The practical setup for imaging an 8 to 10 inch 200 to 250 mm telescope with a modern cooled camera will do well. Larger apertures help, but careful technique matters more. Use short sub-exposures and stack on the comet's motion so the fuzz stays tight while background stars trail. Most stacking software can align on a moving target if you feed it good ephemerides. A high transparency night beats a long one, and a calm mount with accurate tracking beats brute force exposure time. If you're going visual, think 12 inches, 300 mm, or more under Bortle 3 to 2 skies, low power and averted vision. Remember, comets are diffuse, so they punch below their quoted magnitude. Because 3i Atlas is near the Sun in October to November, mind your solar elongation. The sweet spot begins as elongation opens up in early December. From there, plan for pre-dawn sessions, set up while the sky is still in deep twilight. Keep the comet's altitude above any local horizon haze, and wrap before the brightening sky eats your contrast. A slim moon helps. If the moon's fat and nearby, shift to another morning. For field planning, lean on live ephemerides rather than static maps. The JPL Horizons-based tools at the Sky Live will give you nightly positions, rise transit set times, and a rough predicted magnitude curve. They also flag that this is not a fast riser in brightness. Values around 14 to 15 have been typical in October, and aren't expected to plunge into easy binocular territory later. Treat any brighter estimates with skepticism unless confirmed by multiple observers. If you want context while you're out there, NASA's overview page keeps the milestones straight. Perihelion around October, 30, 2025 off-limits from the ground near that date, and back on stage in early December. That cadence matches independent sky-watching outlets, reporting that we'll pick it up again after solar conjunction. Knowing the calendar helps you avoid chasing a ghost on nights when geometry simply won't allow a detection. Even once it's back, temper expectations about a showy tail. The comet's distance from both Earth and the Sun means low surface brightness. Imaging will reveal the coma and any tail structure long before your eye does. If you're after a clean look, choose nights with good seeing, keep your optical train dew-free, and use gentle stretches in processing. This isn't a galaxy with sharp edges, it's a soft, evolving puff that rewards patience more than drama. What happens next is a coordinated dogpile from every wavelength we can throw at it. While 3i Atlas hides in the sun's glare around perihelion, near October 30th, 2025, teams are slotting more ultraviolet time, infrared time and high dispersion optical time so that the moment it peaks out again, the instruments are already pointed. NASA's overview puts the reappearance in early December 2025, which is when the multi-facility campaign picks up from the ground and from space. Ultraviolet comes first because it gives the cleanest water ruler Swift's UV telescope already caught hydroxyl twice, at about 2.9 astronomical units, translating to roughly 40 kilograms of water per second, shockingly early for water to turn on. Expect repeat UV stares after conjunction to track how that OH glow grows, fades or shifts, and to test whether the coma itself, via sun-warmed icy grains, continues to act like a distributed water factory as 3i Atlas recedes. The cadence matters. If OH stays strong while other gases wax and wane, that locks in the grain-driven picture. If it falls off quickly, the surface may be taking over. In the infrared, the priority is carbon dioxide. James Webb's first look found a CO2-dominated coma, with water, CO, water ice, and even faint OCS riding along, and a distinct sunward enhancement that screams active regions. Follow-up spectra will watch whether CO2 keeps leading as geometry and sunlight change, or whether water and CO catch up. That ratio is the key to placing 3i Atlas on a chemical map of its birth disk, since CO2 heavy means formation near a colder CO2 ice line or unusual radiation processing. A swing toward water would hint at layered ices waking in sequence. Wide-angle infrared mapping adds the big picture context. SphereX has already seen an extended CO2 coma and strong signatures of water ice, showing that the gas and grain machinery sprawls far beyond the tiny nucleus. More passes will give time-lapse chemistry. Does the CO2 cloud swell faster than the dust halo? Do ice features deepen or fade? And how symmetric or lopsided does the whole structure become as the Sun-Comet geometry pivots through December and January? On the optical side, high-resolution spectrographs chase the order of operations. The Very Large Telescope watched CN rise only after the ultraviolet water detection and recorded a forest of neutral nickel lines with iron staying quiet, an upside-down combination that hints at gentle, dust-mediated release paths for metals. Extending that series past conjunction will tell us whether CN levels sprint to normal comet values or keep lagging, and whether nickel stays unpaired as activity evolves. A persistent near without Phi signature would be a chemistry gauntlet for models to pick up. Imagers and polarimeters will map the dust physics in slow motion. Early work put 3i Atlas off the usual polarization tracks for solar system comets, implying odd grain sizes or structures. As viewing angles change, those polarization curves should bend in predictable ways if the grains are fluffy aggregates or ice-rich clumps. If they don't, the dust may be coated or compact in a way we rarely see. Meanwhile, deep imaging will probe for an anti-tail, sunward fans, and faint jets that betray where the active patches sit on the nucleus. Tie that to the infrared sunward CO2, and you get a 3D sketch of how gas and dust actually leave the surface. Hubble's job is to keep the nucleus honest. its first constraints pointed to a compact core, effective radius less than approximately 2.8 kilometers, hiding under a bright, dusty coma. Fresh, carefully deconvolved images after conjunction can tighten that size estimate, hunt for hints of rotation, and set limits on fragmentation. If the inner coma profile changes shape between December and January, that may mean evolving jets or even small pieces peeling off. Subtle effects Hubble is built to see. Mars got a front row seat, and that story continues in the data. ESA's ExoMars Trace Gas Orbiter snagged the closest images yet during the October 1st to 7th window as 3I Atlas swept by Mars, and those measurements paired with Earth-side spectra give a unique stereo on how the coma looked from two worlds at once. Expect refined photometry and motion blur-aware stacks from the Mars pass to feed models of dust speeds and jet directions, cross-checked with what we'll record from Earth in December. Timelines on the sky matter for everyone planning nights at the telescope. The comet is behind the Sun through late October and November, then returns to the morning sky in early December. It stays a CCD target, faint, diffuse, and low contrast, but the point is consistency. Repeated, modest exposures beat one heroic attempt. Observers will stack on the comet's motion, log colours for dust reddening, and feed nightly magnitudes into public databases so the global light curve reflects the whole community's eyes. Kinetically, the escape is already scripted. After the solar swing, 3I Atlas climbs outward on its one-and-done hyperbolic path, heading past Jupiter's orbit around March 2026 on its way back to interstellar space. That gives a winter window for follow-ups. UV for water, IR for C, 2, optical for CN and metals, plus deep imaging to chase any changes in tail structure as solar wind conditions shift. The outbound leg is crucial because it tests hysteresis. Does the chemistry shut off in reverse order, or does the coma's memory of all those lofted grains keep water going longer than textbooks predict? All the while, the comparison set keeps expanding. Rubin Observatory's new sky movie is ramping up, and projections suggest it could push us from the era of a handful of interstellar visitors to dozens over its survey, enough for true population studies instead of one-off puzzles. The next time a 3I Atlas announces itself, it won't arrive to an empty lab bench. It will land in a framework of water baselines, CO2 ratios, metal quirks, and dust physics that we're assembling right now, and waiting in the wings is a mission built for exactly this kind of surprise. Comet Interceptor, launching in 2029, will idle at the Sun-Earth L2 point with 3 spacecraft ready to sprint toward the next pristine comet, or the next interstellar visitor, and slice its coma from multiple angles. Every oddity we catalogue in 3I Atlas tells that mission what to measure first, which filters to favour, and how to choreograph a flyby when the alert goes out. Think of what's happening now as building a universal decoder ring for alien comets. With 3I Atlas lighting up water in the ultraviolet while still far from the sun, and with carbon dioxide running the show in the infrared, scientists finally have a set of hard, comparable numbers to plug into the same equations they already use for homegrown comets. That means we can test real, falsifiable ideas. How much water is coming from sun-warmed icy grains versus the surface? How CO2 jets sculpt the dust? How metal atoms get into the gas? On a timeline we can watch night by night, rather than guess from a single snapshot. The plan is to follow the chemistry like a relay race. Ultraviolet catches hydroxyl, the clean fingerprint of water, and sets the baseline for how wet the coma is. Infrared rides herd on CO2, CO, and solid water ice features, mapping which ices are doing the lifting. Optical spectrographs fill in the usual suspects like CN and the surprise lines from metals, while polarimeters watch how dust grains twist and dim the sunlight. Because each band is sensitive to a different piece of physics, the cadence itself becomes the clue. If water stays strong while CN lags and CO2 dominates, the coma factory model wins. If everything snaps into the normal order, the WRFIS is taking back control, There's a second panoramic layer to this. Sphere X is already seeing an extended carbon dioxide cloud hundreds of thousands of kilometres across, a literal gas ocean around 3I Atlas, while James Webb's spectra picked out water ice, gas phase water CO2, and CO in a visibly lopsided sunward-enhanced coma. Put those together and you get not just what's present, but where it's coming from and how it's distributed, which is exactly what you need to separate grain-released water from nucleus vents. The odd metals are a litmus test for gentle physics. Very large telescope data show neutral nickel lines without the usual matching iron early on, implying that some metals are being distilled out of dust or organics by light or mild heating instead of blasted off rock. As 3I Atlas brightens and then fades, teams will track whether iron eventually catches up and whether the nickel-to-iron ratio evolves with distance from the Sun. If nickel leads and iron trails, that points to low-temperature chemistry in the coma. If they move together later, the surface likely opened warmer pathways. Geometry is a free diagnostic. Polarization measurements already nudge 3I Atlas into a weird corner of the dust map, and reports of an anti-tail and a sunward-skewed coma hint that the grain sizes and release times are not business as usual. As the Sun-Comet-Earth angles change in December and January, those same instruments will watch the numbers bend or refuse to bend in ways that tell you whether the grains are fluffy aggregates, ice-rich clumps, or compact coated particles that scatter light in unfamiliar ways. Even the detour behind the Sun ends up helping. While Earth temporarily loses the view near the late October solar swing-by, Mars didn't. ESA's ExoMars Trace Gas Orbiter caught the closest images so far as 3I Atlas raced past Mars in early October. Combining that vantage with Earth-based spectra before and after conjunction gives a stereo dataset on dust speeds and coma shape that we almost never get for an interstellar visitor. All of this is more than a one-off. The era of catching a single interstellar object and arguing about it for a decade is ending. The Vera C. Rubin Observatory's 10-year sky movie is forecast to turn 2 lonely data points into a population, variously estimated from about a dozen over the whole survey to, under optimistic assumptions, many more if we learn to link fast movers better. So the next 3I Atlas moment has a pipeline waiting. With each newcomer, the water yardstick, CO2 ratio, dust polarization, and metal lines can be compared on the same scale instead of starting from scratch. Missions are being tuned around this new reality. ESA's Comet Interceptor will launch in 2029 and loiter at the Sun-Earth L2 point, a 3-spacecraft ambush ready to sprint toward a fresh long period or interstellar target and slice the coma from multiple angles. Lessons from 3I Atlas, like how early water can flare in the UV, how CO2 shapes the coma, and how metals sneak into the gas, feed directly into which filters, what cadence, and how to choreograph a flyby when the next alert hits. On the survey front, NEO Surveyor's mid-infrared eyes are slated to launch no earlier than September 2027, adding a dedicated space-based search for faint, warm dots that ground telescope miss. While its day job is planetary defense, its sweet spot, thermal emission from small bodies, naturally scoops up comets and could catch the warm signatures of distant CO2 active visitors like 3B, I-Atlas as a byproduct, handing targets to Rubin and the rest for rapid follow-up. There's also the origin chase, now that trajectory work and preliminary chemistry let us point outward. Early modelling suggests 3I Atlas may hail from an ancient metal-poor neighbourhood on the border between the Milky Way's thin and thick disks, a region where planet building would stamp very different volatile recipes into its leftovers. If the CO2 heavy signature holds and the nickel-to-iron story keeps misbehaving, that paints a picture of a comet frozen under conditions unlike the Sun's nursery, a relic that carries the smell of another part of the galaxy on its breath. For observers and citizen scientists, this is a chance to feed the machine. Once 3I Atlas clears the Sun and returns to the morning sky, calibrated photometry, coma-aligned image stacks, and polarization estimates from small telescope teams can fill in the nightly light curve and dust behavior between the big observatory's time slots. JPL's horizons and tools built on it provide ephemerides and predicted magnitudes. Sites like the Sky Live wrap those numbers into ready-to-use finder charts, so the community's measurements land exactly where modelers need them. And then there's the question that only time series can answer. Does 3I Atlas remember the heat? If water really comes from swarms of icy grains lofted by CO2, the ultraviolet OH signal could hang on longer than expected on the way out, even as CO2 eases, because those grains keep venting as they coast. A hysteresis you can only catch by watching the outbound leg day after day with the same UV ruler, the same infrared eyes, and the same optical tracers, stitched together into a single living curve. So here we are, standing at the edge of our little neighbourhood, watching a stranger from another sun slip past the porch light. 3I Atlas didn't ask for permission, didn't slow down to pose, and still managed to rewrite lines in a book we thought we knew by heart. It came from the dark with a chemistry that doesn't match our expectations, and a habit of turning water on where water shouldn't dare. And somehow, in its brief visit, it reminded us that discovery isn't neat. It's messy, surprising, and a little bit wild. If this journey lit up your curiosity, don't let it fade with the end screen. Tell me what grabbed you most. Was it the early water, caught in ultraviolet like a secret note only space can read? The carbon dioxide calling the shots? The odd metals, the strange dust? The anti-tail geometry that made even veteran comet watchers blink? Drop your thoughts below. I read them, I learn from them, and sometimes your questions become the seed of the next chapter. For those of you who aim your own glass at the sky, this visitor is shy, not showy. It's a low-contrast whisper that rewards patience and careful technique. Check fresh charts, stack your frames on the comet's motion, and share what you capture with your local club and with the world. Every honest attempt, every faint smear coaxed from the background adds a pixel to the picture we're building together. And for the rest of us who explore with headphones and a warm drink, let the idea sink in that right now, above you, there's a small ancient body releasing the breath of a place our eyes may never see. The water you just heard about was frozen under a different star. The dust drifting off that nucleus learned to scatter light in another nursery. When it passes, it will take its stories back into the dark, but not before we borrow a few pages. If you want more deep dives like this, more strange truths, more quiet wonder, tap subscribe and ring the bell so you don't miss what's next. I'm lining up follow-ups as new data roll in. How astronomers smell water from orbit, why carbon dioxide can run a comet from the cold, what polarization tells us about alien dust, and what missions like Comet Interceptor are preparing to do when the next interstellar traveller drops by unannounced. If this episode helped you see the night with fresh eyes, consider sharing it with a friend who needs a reason to look up. It helps more than you think. If you'd like to support the channel, you'll find links below. But honestly, the best support is your curiosity. Bring it back, bring your questions, your doubts, your wait, how do we know that? That's the fuel! 3I Atlas won't be here long. It's already leaning toward the outbound road, past the glow of our sun and into the long hush between stars. But for a little while, we get to listen. We get to measure. We get to marvel. And then we do what humans have always done. We keep watch for the next flicker, the next whisper, the next uninvited miracle crossing the yard at the speed of wonder. Thank you for spending part of your night with me. I'll see you in the next one.